Okay. Hello, my name is Florian Murr. I'm working for the Siemens AG, and I'm talking about McFSM, which is an acronym for Multiple Coupled Finite State Machines, and it extends the applicability of finite state machines. If you look at large systems, then you see that they often use objects and messaging, and they form implicit global data structures and algorithms. And that's a problem, because we usually only have a local view onto the objects and the messages and do not see the global data structures and algorithms because they are implicitly coming from these structures. So we try now to make the structures explicit and have a global view onto the data structures and the algorithms they form. McFSM is an explicit global view onto objects and their interactions. And to understand where the McFSM fits in, let's have a look at finite state machines. Finite state machines have many advantages. They are everywhere. And one of the advantages is they do not have any runtime secrets, which means we can prove everything at compile time. And there is usually no need to resort to testing because you can prove the required properties straight from the properties of the finite state machine. The finite state machine is on the left side of a continuum of different languages and machines. On the right side, we have the Turing machines. And there is some difference in expressive power. The expressive power of Turing machines is much bigger than that of finite state machines. But on the other hand, the provability goes straight down. So with a Turing machine, you can express everything, but you can prove nothing. And that's the major problem of Turing machines. And the McFSM tries to be in the middle. It tries to extend the power of the finite state machines so that we can do things you usually used to do Turing-complete code now with finite state machines. The McFSM can handle huge finite state machines, and thereby greatly extending the range of applicability and while retaining their advantages. A look at finite state machines, it's something like that. It's very simple. Usually I do not have to tell you, you all know. You have states and state transitions, and I just have that there that you have a glimpse of the domain-specific language I developed. It's on the left-hand side. Actually, it's TclOO code that has some internal interpretation magic to cope with things. I do not go into that now. We do not have the time, but if you're interested, we can talk about that later. You have to bear in mind that finite state machines are theoretical constructs, and they may be really huge. So the diagram that you see here, where you have the explicit states and the state transitions, might not be possible if the finite state machine is huge, because it just wouldn't fit into any memory. We have a graphical notation for finite state machines. Usually you have something like this. You have states and you have transitions. And there you have the name for the finite state machine, and you indicate some start state or some start node. And then you have the input events, and they are, in my diagrams, they are depicted in blue and above the edges. And we have output events that are below the edges. And that is a bit unusual to have output events, but we need them for the mechanism I want to show you. As I said before, McFSM stands for multiple coupled finite state machines. We coupled the finite state machines via internal events. That is, the state transitions themselves are considered to be events. Let's have a look at these three finite state machines. The ones on top, the finite state machine 1 and 2, are quite ordinary. You can think of something like a switch. You can make the switch up and down. And on the on bottom, the finite state machine 3, you can think of something like a status indicator with G for green and Y for yellow and R for red. The finite state machines 1 and 2 would react on external events, in this case x0, 1, 2, 3, and they publish their outputs via events f0 and f1. I have written here there publish because I really use the publish subscribe pattern, and I have another slide where I can show you the difference between the observer pattern and the publish subscribe pattern. Really, the observer pattern is, in my opinion, very flawed in many places, and the publish subscribe pattern behaves more benign. And actually, the problems with the observer pattern were the initial cause why I invented the McFSMs in the first place. So the finite state machine 3 has as events that it reacts on the output events of the first ones. So the comma between f0 and f1 means either f0 or f1 if the finite state machine 3 happens to be in the state G, and either f0 or f1 happens, then it will go to the next state. We can view the finite state machines as opaque entities as well. That is one of the mechanisms I devised for reasoning about it. I just sketch it here because there are many more details and there are different ways of other ways of doing it that I will not present. If you view the finite state machine 1, 2, and 3 as a single node, as seen on the right side, and you connect the nodes if one finite state machine issues or outputs an event that another finite state machine consumes, you get the graph on the right-hand side. It's a very small graph, and because this graph, which I dubbed K1 for something like concentrated or automaton, this graph is acyclic, and because it has no cycles, I can conclude from that the coupled finite state machine works, that it behaves benignly. Actually, if you are coupling completely freely the finite state machines, it is theoretically possible to construct a coupling that would result in a distribution of internal events that does not end. So you have to be able to predict at compile time how many steps it takes. If you have an external event, it goes to the finite state machines inside, and they publish their internal events, and you have some machinery internally that distributes these events. This internal machinery is actually a stack. I will come to that later on. And you have to be sure that this internal event distribution is finished after a few steps, and you have to predict these steps. And the cycle freeness of this graph K1 is one way to reason about it and to make sure that this will always be possible, and I call McFSM that has this property to be well defined. If it's not well defined, then I cannot decide at compile time whether an event will be processed with finite steps. Okay, here now you see what I said before. I recognized that there is something like, if you have non-recursive functions and recursive functions, and that the same holds between finite state machines and the coupled finite state machines. It is really like extending the semantics as you do from non-recursive functions to recursive functions. Here you are extending it in the same way from ordinary finite state machines to the coupled versions. Actually, the McFSM have the same construction and semantics. That's really something new, because I looked a lot in all the alternative tools and things. Especially UML has some state machines inside it that could do things like the coupling, but there they do not have any word about the semantics and how the distribution is to be done. And that is really the key point. If you do not specify that, you cannot reason at all. So that is the reason why I consider the McFSM approach to be a new approach. The events can be viewed as method calls to a finite state machine object. Usually the event function is called delta in literature. And if you have an ordinary function like f on the left-hand side, you can see that with a recursive function, the function f triggers this sequence of internal calls. Likewise, in a McFSM, some event E0 might trigger a sequence of internal events. When you have it recursive, then the GHI function may call f again somehow. And this is mirrored on the right-hand side with the McFSM. It might behave recursively. The internal events may call the delta function again, so you have again the same recursive mechanism. You have to preserve the order of G, H, and I, and likewise you have to preserve the order of the events in which they arrive. You have to do run to completion. You have to finish G before starting H, and the run to completion is mirrored on the side of the McFSM as well. And if you have these two properties, that you preserve the order of events and you have run to completion, then you get then you need a stack in between to mediate all that. For historical reasons, the stack is called XQ because I started with the Q property and extended it, and so the name XQ stuck for this internal mechanism. But if you look at it from the properties it has, then you will see that the Q property is not so important as the stack property, because the Q will only have a finite number of entries. Maximum will be all the finite state machines, and the stack property is really the one where we have to have a closer look that it really terminates and only uses a finite number of steps. I'm developing an IDE for the McFSMs, or I dubbed it McGen, and it is currently like that. The McGen is the red one, and I developed a DSL, domain-specific language, as I mentioned before. And the McFSM has a web server inside where it provides the documentation for itself. So if you have the star pack, you can see everything, how to use it. Actually, keeping the documentation in sync with my implementation is proving hard because I change my mind so frequently. And okay, but from the architectural point of view, it's all in there. And out of the DSL, I generate the finite state machines in different languages. Currently, only the green ones are provided. That's TcL and C++. But there might be anything else, as I indicated here, especially protobuf, Google Protocol buffers for communication and things like that. And all the internal data structures that I get from the parsing and which I derive through calculations in MacGen, I put it all into an SQLite file. So in the SQLite file, there is the configuration options, there is the text form that I read from the DSL, there is everything I get from the parsing from the DSL, and everything I calculate, it's all in the SQLite file. So if somebody wants to provide some different backend or do some reasoning about it, he does not need to change to do the parsing again. That means I can change the DSL slightly and things like that because the SQLite should provide all the required information, and one should be able to put on top of it whatever you like, and you can use any language you like if you have reasons not to use TcL. Actually, defining finite state machines from scratch is cumbersome sometimes. And therefore, I'm currently working on a plug-in interface where you can use almost any data structure as a finite state machine. Let's look at finite stack. It's just you have a stack and you want to use it like a finite state machine in this environment. Then you have first to make it finite. So let's introduce some maximum fill state value for the stack. And if you have it connected with the other elements of in the IDE with the other finite state machines, you at compile time you know all the elements that could go in there. So there's nothing hidden. You know which elements are connected with the coupling, so which might go into that. You have a maximum, so it's a finite structure, and everything is really a finite state machine as such. If you look what something like that looks like, let's take an instance of this finite stack. Say maximum is 5. Then you have some mental image like that. You know you can push things on it, and you can pop elements from it, and that it behaves like that. I'm trying really that the plug-in interface should capture that also, that for very small values like maximum equals 5, you have the IDE has the same knowledge about what a stack is supposed to do as you have as a programmer. And when we look at the output events, you have a similar mental image where you can see how the output events are connected. When you want to use bigger structures, like where the maximum is bigger, then the finite stack would represent a finite state machine that is so huge that you cannot represent it as such, but you can captures the class information like that. So you have something, you have a state, something like it's empty, or it has elements, or it is full, and you have the transition between these different states, and that is, so we have on the one hand side for very small instances, we can really represent the instance as it is via this plugin interface. Actually, I'm not absolutely sure whether it's possible because I'm not quite finished with that. And on the other hand, we have a representation how all finite stacks should behave. And all this is communicated through this plugin interface to the IDE. So you could then use any implementation you have for a stack, call it a finite stack, plug it into this interface, and provide the information to the IDE. And the IDE can use it as any other finite state machine in this whole environment. With this interface, it should be able to, we should be able to really use any data structure and make it finite and use it as a finite state machine. We can reason about that at compile time, and the conclusion is, I just borrow an expression from Saint-Exupéry. Perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. That's really the TclOO philosophy. It is make it as simple as possible. And the finite state machines are absolutely simple data structures, and the coupling is a very simple idea. And to make it work powerfully together, and as Donald said before we went to the lunch, that if something is prohibited, it should have a good reason for that. So here it is really two simple ideas combined and extended in a way that you can do almost everything with it. So McFSMs is a simple and powerful tool to model global system structures. And what distinguishes McFSM from other approaches is it's a very concise thought model. You combine finite state machines and PubSub, publish, subscribe. You carry the power of recursive functions into the realm of finite state machines via the stack XQ. The simplicity of all that leads to a theory that allows mathematical proofs. And this extends the finite state machines to really huge state spaces and makes them trackable. Any data structure can become a finite state machine via the plugin interface. And we have a lean domain-specific language emphasizing PubSub and recursive function. Thank you. That's it basically. You can I skip through this stuff. That is something, that's a glimpse on my user interface I can show you later on. And I can really say anti-aliasing should be part of TK and not of some extension. So I can show you the thing of working in later on, and we can discuss about the details, but that's the basic idea of the whole that. And I want to make it public domain in this fiscal year. Do not know yet where and how, but I think you should be able in a few months to download it and experiment with yourself. And actually, there might be quite a few things that are not working as expected. Then just give me an email and I will fix it. That's it. Any questions? Yeah.
When you say that the coupled finite state machines are somehow similar to recursive functions, I'm asking, is as far as I know, recursive functions are Turing-complete. But you say your finite state machines coupled are still provable. So how does it come to fit together?
Because with recursive functions, usually you have no limit on how far the stack grows. And actually, that is something that I try to prevent in the IDE. There you have a look at the coupling on the stack, and you can see if there is some event where it might have an infinite growing stack, and stack growing above a number of steps that you provide beforehand. Because if you want to use it in real-time applications, then you want to make sure that after, let's say, 5 steps or 10 steps, every event is processed completely. And so you must be able to limit that. And the IDE is really meant to let you inspect how many steps it takes for every event to be processed, and which other events get triggered by any event, so that you really have a global view onto the entire system. Actually, currently, the McFSMs are especially for things that run in one process, so in multiple threads or something like that. At the moment, it is not even in multiple threads, it is really one thread. But I want to extend that for multiple threads and for distributed environments and things like that. And it all comes always down to that you really have to look on the system as a whole. Not how does one element of it behave, how behaves it if I plug it together. So, that's the idea. And to make any reasoning possible at compile time, I have to impose limits. And my limit is it must be a finite state machine. Yeah.
Question. Because you have state machine that manage the states, so it's a kind of context that you record somewhere in the program. When you launch the program, does it take into account an external context, or should it start from the initial states?
The initial states that can be configured.
Yeah.
So it is not, actually I have a class concept here where you can write a class for a finite state machine, and then you have different instances, and every instance has a different start state. So the class as such is the finite state machine without an initial state. It might be any of them. You have just the behavior, but the instances you make from the finite state machines, they can have different start states, and with that you can configure what you really need. And you must be able to check the correct behavior for every possible start state.
I would like to stop the discussion now, because we are a little bit late in time. I think you will be able to give detailed questions in the breaks or at lunch, at dinner tonight. So
okay.
Again, thank you.